Good evening to all of you. Today's lecture is focused on microwave remote sensing. Particularly, we will be discussing SAR remote sensing in detail. So, we already have the information of basics of remote sensing and its application. Now, we will going in detail of SAR remote sensing. So first of all, as we are knowing that each and every remote sensing technique is based on the electromagnetic radiation. So we are going to start with the electromagnetic radiation. So electromagnetic radiation consists of an electrical field which varies in magnitude in a direction perpendicular to the direction in which the radiation is traveling, and a magnetic field M oriented at right angles to the electric field. Both these fields travel at the speed of light. Here in this diagram we can see that E is representing the electric field vector, M is representing the magnetic field vector. Both are perpendicular to each other and mutually perpendicular to the direction of propagation of electromagnetic wave, that is C. This is the very famous formula representing the relation between wavelength and frequency. The wavelength is the length of the one wave cycle which can be measured as the distance between successive wave crests. Wavelength is usually represented by the Greek letter lambda. Here in this diagram, it can be easily seen that the distance between two successive peaks will be the wavelength of the electromagnetic wave. So here this lambda is representing the wavelength. And from the relation, it can be easily seen that longer the wavelength, smaller will be the frequency, and higher the frequency, smaller will be the wavelength. We are talking about the microwave remote sensing. So one can think that what is microwave remote sensing? Yeah, remote sensing, each and everyone is knowing that, okay, remote sensing is the technique in which you utilizing the concept of electromagnetic scattering, reflection, emission. One will be able to extract the information of any object without touching the object or without getting in touch with the object. So again, this remote sensing technique is subdivided in different category, and one category is microwave remote sensing. So one can ask that, okay, what is microwave remote sensing? So from the name it is clear that the remote sensing which is carried in the microwave region of electromagnetic spectrum is known as microwave remote sensing. So in microwave remote sensing, the wavelength region 1 millimeter to 100 centimeter of electromagnetic spectrum is used in this remote sensing technique. So here in this figure, it can be easily seen that the wavelength region is starting from K band. Yeah, some smaller wavelengths are also there, but mainly we are talking from the K band. So Ka band, K band, Ku, then X band, C band, then S band, L band, and P band. These are the main bands used for the remote sensing. And when you will see each and every band, or you can say sub band of microwave band, will have its own wavelength range. Like in the case of K band, you can see it is 0.75 to 1.1 centimeter, and for Ku band it is approximately 1.67 to 2.6 centimeter, 2.4 centimeter, and in the case of X band it is 2.4 to 3.75 centimeter, and for C band it is 3.75 to 7.5 centimeter, and similarly different wavelength regions for the different wavelength ranges and different bands. So what we are seeing here, when we are moving from K band to P band, there is increase in wavelength. It means that when we are moving from K band to P band, there will be decrease in frequency but increase in wavelength. So for each and every wavelength region, uh, there will be a separate sensor. Suppose a radar sensor is configured to work with C band, so that particular sensor will be providing the data set in C band only. It is not going to provide the data set in S band, L band, P band or K band. It will be providing only the data set in C band. Similarly, if a sensor is designed for L band, so it will be providing the data set in L band only. There are different advantages and disadvantages of different bands, so that this microwave band, the microwave region, is subdivided in separate bands. Now, here again, in more clear view, the same bands are given here with their wavelength and the frequency range. Like in the case of Ka band, also known as K above, we will have the wavelength region from 0.75 to 1.1, and frequency ranges in gigahertz 26.5 gigahertz to 40 gigahertz. And similarly, you can see that when you are increasing the wavelength, there will be decrease in frequency from K band to P band. P band will have the longest wavelength but smallest frequency in this radio wave. When we are talking about the microwave remote sensing, there are different kinds of sensor. So one famous sensor is there, that is radiometer. So radiometer is a kind of passive sensor. So question is, what is passive sensor? A passive microwave sensor detects the naturally emitted microwave energy within its field of view. This emitted energy is related to the temperature and the moisture properties of the emitting object or surface. And all the passive microwave sensors are known as radiometers. There are several applications. Applications of the passive microwave remote sensing include the meteorology, hydrology, and oceanography. The microwave energy recorded by a passive sensor can be emitted by the atmosphere, reflected from the atmosphere, emitted from the surface, or transmitted from the subsurface. So, radiometer is the only example of passive microwave sensor. Remaining sensors are active sensors. As in the basics of remote sensing, we have already learned about the active and passive sensors. So passive sensors are those sensors which cannot generate their own energy, and these sensors are dependent on another source of energy. And active sensors can generate their own energy. So radiometer is the passive sensor in microwave region, or we can say the passive microwave sensor. When we are talking about the active microwave sensors can generate their own energy, can transmit the electromagnetic pulses, and those pulses can be recorded after interaction with the earth object or any object appearing on the surface. And finally, these active microwave sensors are again subdivided into categories: imaging and non-imaging. So first we will be talking on the imaging sensor, because this lecture is mainly focused on imaging microwave sensors. The most common form of imaging active microwave sensor is radar, and we all are knowing that radar is an acronym for radio detection and ranging. So the radar sensors transmit the electromagnetic pulses or radio waves in between 1 millimeter to 100 centimeter. The sensor transmits a microwave signal towards the target and detects the back scattered portion of the signal. Back scattered here because when any electromagnetic wave will interact with any object, then different kind of phenomena will occur. Some portion will be reflected, some portion will be absorbed, some portion will be scattered. So here in the microwave remote sensing, we are mainly dealing with the scattering, and finally the sensor is receiving the back scattered portion of the signal. Back scattered is simply receiving the amount of scattered energy which returns back to us the sensor. This is the back scattering. We will be seeing the graphical representation of these things in the next slides. Now after talking about the imaging sensors, we are coming to the non-imaging microwave sensors. So non-microwave imaging sensors includes altimeters and spectrometers. In most cases, these are profiling devices which take measurements in one linear dimension, and due to one linear dimension, they are simply the profiling devices. They cannot be represent, they cannot show any image as opposed to the two-dimensional representation of the imaging sensor, because imaging sensors there will be two-dimensional representation. Radar altimetry is used on aircraft for altitude determination and on aircraft and satellites for topographic mapping and sea surface height estimation. From the name altimeter, it is clear that it is mainly measuring the altitude, and spectrometers are also generally non-imaging sensors and are used to make precise quantitative measurements of the amount of energy backscattered from the targets. There are several applications of spectrometer, mainly for the marine application to find out the wind direction, wind speed, and tide information. So spectrometers are also used as non-imaging sensor. Here there is a comparative table between LIDAR, optical multispectral, and SAR. So when we are talking about the LIDAR, mainly airborne LIDAR remote sensing is possible. Here from space-borne remote sensing is also possible, but currently not a single sensor is available, but archived data set of large sensor is available. And like in future, NASA is going to launch another sensor with another satellite with LIDAR sensor. So at that time, airborne and spaceborne both will be possible with LIDAR, and optical multispectral. This can be done with the help of airborne and spaceborne, both the platforms. And SAR, definitely it can also be done on the basis using both the platforms, airborne and spaceborne. Radiation, since LIDAR is an example of active sensor, so it can generate its own radiation. And optical multispectral are passive sensors. They are basically dependent on the reflected sunlight, and SAR is an active sensor and it can generate own radiation. Now spectrum, when we are talking spectrum, means here we are talking about the portion of electromagnetic spectrum. So LIDAR uses infrared region of electromagnetic spectrum, optical uses visible and near infrared, and SAR uses microwave region of electromagnetic spectrum. Frequency, LIDAR, this is operated on single frequency. Optical multispectral, from the name it is clear, multispectral, it means that multi-frequency will be there. When we will have more than one spectra, then definitely we are talking about multispectral. SAR, multi-frequency, yeah, it is possible multi-frequency, but one sensor can be designed for one frequency range only. So to get the multi-frequency data set, we must have the multi-SAR sensors. Multi-SAR sensor means more than one sensor should be there at the platform, then only we will be able to get multi-frequency. Currently, not a single space-borne SAR system is working in this multi-frequency system. Yeah, airborne experimental SAR systems can be operated on multi-frequency. Polarimetry, due to small wavelengths, currently not possible in LIDAR and optical multispectral. But polarimetry and polarimetric applications are possible in SAR remote sensing. Similarly, interferometry is not possible in LIDAR and optical multispectral, but it is possible in SAR remote sensing. These two are the major advantages of SAR remote sensing over other remote sensing techniques, because using polarimetry and interferometry, one will be able to extract the different properties of the objects. Using interferometry, one will be able to get the information of the height also. One can generate the DM also. There are several applications. And if you are talking about the acquisition, so this can work in the night time. LIDAR remote sensing can be done in the night time also, so it will have the night vision capability. Optical multispectral cannot be done in night time, so because this optical multispectral is an example of passive remote sensing, it is completely dependent on the reflected sunlight. So in daytime only we will have the information, and if anyone will be interested to get the information at the night time, so either LIDAR or SAR dataset can be used because both the sensors will have the night vision capability. Both the sensors can be operated in daytime as well as in night time also. Now, when we are talking about the weather, so to extract the information at the time of cloudy situation, when the clouds will be there in the troposphere or for the tropical region, most of the times clouds will be there in the atmosphere. So particularly for that time period, radar remote sensing cannot work, cannot provide any information below cloud cover because it will completely blocked by the cloud. Similar thing will occur in the case of optical multispectral also due to small wavelengths. They will be completely blocked by the cloud particles. Now, when we will see the SAR remote sensing, so in the previous slides, we have seen the wavelength region. So in the case of when we will go to the previous slides, when you will see the mainly the space-bound remote sensing, we are doing with X band, X, C, L, and P. So starting from X band, if you will see, this is in centimeter, and this is larger than the cloud particle size. So finally, this wavelength or larger wavelengths more than X band or X band, uh, this wavelength region can easily penetrate the cloud cover or top cloud cover. And finally, if one will be interested to extract the information below cloud cover in the time of rainy season also, then this data set may be utilized to extract the information of different objects appearing on the earth's surface in the rainy season. So we have seen the advantages advantages and disadvantages of different remote sensing techniques. Yeah, but optical multispectral, since our eyes are sensitive for the visible region, so this particular wavelength region for multispectral is very good for the visualization. No one can replace the optical multispectral for the visualization, but to overcome the limitation of this multispectral light for the night vision capability, and to take the advantage of polarimetry and polarimetry interferometry, and the information at the time of cloud season, or information for the tropical region, then one may be interested to use the SAR remote sensing. This is the list of satellites, and detailed list is also added at the in the last of the slides. So if anyone will be interested to go in the detailed information of all the SAR satellite missions, so one can see those slides. These are the famous missions like RISAT-1. This was launched in April 2012, and this provides the data set in C-band, and here also this can also provide the data set in quad pole mode. RADARSAT-1, this one launched in 1995, currently not working. It provided the data set in C-band. RADARSAT-2, RISAT-1 is the name of the radar imaging satellite. This is the Indian satellite mission providing the data set in C-band. RADARSAT is the radar sensor series of Canadian Space Research Center. So RADARSAT-1 was launched in 1995, and RADARSAT-2 was launched in 2007. And this is also a kind of advanced SAR system. It provides the data set in quad pole mode in C-band only. ERS-1 and ERS-2 both were launched by European Space Agency to extract the information of the Earth's surface, and both were working in the C-band. JERS was launched in 1992, and it was providing the data set in L-band. Another satellite, InviSat, this was launched in 2002 by a European Space Agency, and it provided the data set in C-band. And ELOS, previously the name was ELOS-1, and now ELOS-2 is in working condition. So ELOS Pulsar is the name of the sensor. So ELOS Pulsar is providing the data set in L-band. So for ELOS Pulsar 1, archive data set is available, and for ALOS Pulsar 2 the current data set is also available. This was launched by Japanese Space Research Center, Japanese Space Agency, and TerraSAR X and Tandem X. These two satellites, TerraSAR X and Tandem X, both were launched by German Space Agency, and it provides the data set in X band. Now, after getting the information of the different SAR sensors, now we are going to move on radar geometry. Why? Because the terms used in radar geometry are very much important for SAR data processing. If one will be getting the data set, then definitely the person will be in need to process the data set. So nowadays softwares are capable to provide the data set, but sometimes if they will not have the information on the software, or softwares will not be there for the newly launched satellite, if the softwares are not supporting, then one will be in need to know these parameters to process the data set. So there are some geometrical terms. We will be going in detail of the radar geometry. So here you can see the aircraft is there, and at the bottom of the aircraft SAR sensor is placed. So if you will see this uh, aircraft, so aircraft is moving in one direction. So the direction of flight is known as azimuth direction. Azimuth direction. Now the SAR sensors, all the SAR sensors are side looking radar systems. Here sometimes I am using SAR, sometimes I am using radar. So in the next few slides I will be going in detail why I am saying sometimes SARs. SAR is generally synthetic aperture radar. Why I am saying radar, so we will go in detail. So don't be confused with the name radar and SAR. Whatever I am saying, that is related to the radar sensor only. So this radar sensor will be looking in one direction. It will be either looking left or right according to the azimuth flight direction. So here in this case, the radar sensor is looking left. When you will see this direction, radar sensor is looking left. It is transmitting the electromagnetic pulses. So the range in which the radar sensor is looking, that will be either left or right, that will be known as the look direction or range direction. And here if you can see, suppose the radar sensor or SAR sensor transmitted the electromagnetic pulses and this much area was illuminated, this much portion was illuminated. So the portion of illuminated area which is appearing or lying near to the nadir point, near to the nadir, that will be known as near range. It is written also, it is written near range. The portion of illuminated area which is appearing near to the nadir will be near range, and away from the nadir will be far range. Similarly, if you will see the angle of incidence, now we are going to talk about the angle of incidence. So angle of incidence will be the angle between the uh, transmitted electromagnetic pulse and a perpendicular drawn to the point of contact. So the angle between this perpendicular at the point of incidence and the transmitted electromagnetic pulse will be showing, or incident electromagnetic pulse will be representing angle of incidence. So here you can see, when we are talking about the near range, means the point which is near to the nadir. So near range, there will be one angle of incidence and another angle of incidence, some different kind of value will be there for the angle of incidence in the far range. It means that angle of incidence for each and every location, for each and every pixel will be different, will be varying. It means that the angle of incidence will be varying from near range to far range. And another term is angle of depression. So the angle made between the look direction to the transmitted electromagnetic pulses will be showing the depression angle. And when we are talking about another term, that is the look angle. So in the next slide it will become more clear. So look angle, angle between the nadir line and the transmitted electromagnetic pulse will be showing the look angle. So if you correlate with the previous slide, this will be the look angle. So look angle will be varying from near range to far range. And from the geometry it is clear that for the flat terrain, look angle will be exactly equal to the angle of incidence, and the depression angle will be 90° minus angle of incidence, or 90° minus look angle. So the SAR sensors will have the information of this look angle for each and every pixel, because for each and every pixel this look angle will have its own value, because the look angle will be varying from near to far range. Now, when we are talking about the radar sensor, then what is the need to say the SAR, synthetic aperture radar? Yeah, when radar sensor is used, then why we are saying it as SAR or synthetic aperture radar? Definitely there must be some reason. So here, in this case, when we are talking about the resolution, so there are two resolutions. One will be azimuth resolution and there will be the range resolution. It means that single SAR resolution cell will have two resolutions. One will be azimuth resolution, another will be range resolution. Now, to this azimuth resolution is directly related to the antenna length, and to place a very large antenna in the space is practically impossible. Antenna of several kilometers in present scenario, practically it is impossible. So scientists utilized the speed of spacecraft to synthesize the antenna length. It means that they generated a virtual antenna of long length with the help of small actual antenna. Like in this case, if you are able to see this point target, so suppose the radar sensor starts transmitting the pulses from this location, and we are expecting that before that SAR sensor was not able to capture any information of this point target. Suppose from this location it started getting the information of this point target, and radar sensor transmit the electromagnetic pulses, and those pulses after interacting with the earth surface return back towards the SAR sensor. So suppose after interaction the pulses were the return pulses or back scattered signals were returned back toward the sensor and finally converted into an image, and the signal was captured. So the SAR sensor is moving in azimuth direction. So for each and every time it is continuously transmitting electromagnetic pulses and recording those pulses after scattering from this point target. So for this particular point target, suppose this is the last point, after this point the SAR sensor will not be able to capture any information for this point target. So from this distance to this distance, SAR sensor transmitted the electromagnetic pulses from several locations from the several time period and captured the return signals. It means that the whole length or the whole distance captured by the sensor will behave like a synthetic antenna, or you can say will behave like antenna for this point target. So from this we can say that the antenna length will become very large, because the number of returns were continuously captured by the sensor from the time t1 to time tn. So one can easily find out the synthetic aperture length from the radar geometry. So suppose if small LA, this small LA representing the actual antenna length. So if small LA is known and this range distance is recorded in the terms of nanoseconds, means the time taken by the electromagnetic wave to uh, uh, to capture the information of this target. It means that it will have the it will be represented by the two-way propagation of the electromagnetic wave. So finally the time will be recorded in nanoseconds, and when you will multiply it with the speed of light divided by 2, you will have the information of this range distance. Range distance is simply the distance from sensor to the point target. And when you will use this formula, one will be able to get the synthetic aperture length of the antenna, R naught multiplied by lambda divided by LA, where R naught is the range distance between the target and the antenna, antenna, and lambda is representing the wavelength used in particular micro remote sensing, and LA is representing the actual antenna length. One will be able to get the synthetic aperture length of the antenna. Why we did this? To enhance the azimuth resolution. Now when we will have the information of the range distances, one can easily find out the total ground swath width. So total ground swath width can be determined with the help of this formula, that is RF minus RN divided by sine phi, where phi is the mean angle of incidence and RF is representing the range distance, or you can say far range distance, and Rn is representing near range distance. So one will be able to get the information of the ground swath. Now again, when we are talking about the resolution, azimuth resolution, as we have already talked, since the SAR sensor is moving in the azimuth direction and transmitting the pulses in range direction, so each and every resolution cell of radar image or SAR image will have the two resolutions. One will be azimuth resolution, another will be range resolution. So azimuth resolution is the length of the resolution cell in azimuth direction. Like we can understand with the help of the previous image. Suppose the whole cell is representing one resolution cell. Suppose the whole cell is representing one resolution cell. So this length is the length of resolution cell in azimuth direction. So this length will be known as azimuth resolution. And the range resolution is the length of resolution cell in the range direction, or the direction in which the radar sensor is transmitting the pulses. So this is the direction in which radar sensor is transmitting the electromagnetic pulses. So this length will be known as a range resolution. So now I think this will become clear. Each and every resolution cell of the SAR sensor will have the two resolutions. One will be azimuth resolution, another will be range resolution. Azimuth resolution describes the ability of an imaging radar to separate two closely spaced scatterers in the direction parallel to the motion vector of the sensor, or we can say that in the azimuth direction. Range resolution, similarly, for the radar to be able to distinguish two closely spaced elements, their echoes must necessarily be received at different times. If the time will be very less in the return signals, then it will be very difficult to detect as two separate objects. So, range resolution is also defined on the basis of their pulse width. The yeah, we will see the relation in the next few slides. So first we will be talking about the azimuth resolution. So azimuth resolution is simply the product of the effective horizontal beam width and the slant range distance to the target. So here you can see RA, this is the azimuth resolution, is equals to R. Don't be confused with R naught and R. Both are same. R is basically R naught, that is the range distance, R lambda divided by 2L. Now you can see when this antenna length will be increasing, this amount will be decreasing, and finally azimuth resolution will become very high. So longer the antenna length, higher will be the azimuth resolution. Now again going to the range resolution. Now we have already talked about azimuth resolution and its concept and all these things. Now coming to the range resolution. Range resolution is the minimum range difference for which 2-point targets are recognized as two separate objects. Otherwise, if the sensor will not be able to identify the two closely spaced objects, then both the 2 points will be detected as one point. So range resolution is defined in the terms of pulse width. So if a sensor will have the tau pulse width, so its range resolution should be more than c tau divided by 2. It means that any object which will be having, means if the two objects will be separated by this distance or more than this distance, then those two objects will be appearing as two separate objects, and if the distance between the two objects will be less than this amount, then both the objects will be merged and finally appear as one object in the SAR imagery. It means that SAR sensor will not be able to capture them as two separate objects. At that time both will be captured as one object. You can understand the same with another example. Now here you can see the pulse width tau is 1 microsecond. So tau is 1 microsecond. So C tau will be totally 300 meter. Hence the range resolution for this radar system will be C tau divided by 2. It means that this will become 150 meter. Now see the first image here. The distance between the nose of this aircraft to the nose of the another aircraft is 100 meter. It means that these two aircrafts will be appearing as only one object in the radar imagery, because its range resolution is 150 meter and this 100 meter is less than 150 meter. It means that both will be appearing as one object in the radar imagery or SAR imagery. Now here in this case, the distance between the nose of the first aircraft to the nose of the second aircraft is 200 meter. It means that this is greater than 150 meter. It means that this distance is greater than the minimum amount of range resolution or the range resolution 150 meter. It means that both the aircrafts will be identified as two separate objects or two different objects in the SAR imagery or radar imagery. Now when we are coming to the slant range and ground range, so due to because SAR sensor is transmitting the electromagnetic pulses in range direction, or we can say that in slant range. So due to slant range ambiguity, objects appearing in near range, we can see in this graphical representation, objects appearing the distance between the different objects A, B, C, D, E, F, G, H. Now what we are seeing, the upper image is showing the appearance of the objects or the distances in the SAR imagery. So a real earth or ground range information is this one, and its appearance on the SAR imagery this one. So what we are observing, the objects appearing in near range are compressed or not represented by their actual shape or size in the SAR imagery. And what we are seeing, that when the objects are near, compression is very high, and we are moving from near to far range, so towards far range compression is very less. It means that the compression will be very high in the near range and it will be very less in the far range. So to get the actual ground information after getting the SAR data set, one should do the slant to ground range conversion, because there will be slant range ambiguity in the SAR imagery, and our first job should be to remove the ambiguity due to this slant range, and finally we should be able to do the slant to ground range conversion, and this conversion can be done with the help of angle of incidence. If the angle of incidence is known, then the range resolution multiplied by 1 divided sine of angle of incidence will be giving the information of ground range, and finally it will be converted to the ground range. When we will see the SAR data, this is the SAR data set of TerraSAR X for Visakhapatnam port. So this data set is freely available on the website of TerraSAR X, and one can download and process this data set also. So radar sensor captures the information of the return signals, or we can say the information of the backscatter signals. The radar returns from the terrain are mainly determined by the physical characteristic of the surface features, such as surface roughness, geometric structure, and orientation. The electrical characteristic, dielectric constant, moisture content, and conductivity, and the radar frequency of the sensor. Because when these will be changing, either wavelength, moisture condition, dielectric constant, and structural information, then the radar backscatter signal will also be changing or will also be affected. So one can say that the backscatter is a property of surface roughness and dielectric constant, mainly the structural property and dielectric property. Backscatter property is changing due to the structural and the dielectric property of the object. And SAR data consists of high resolution reflected returns of radar frequency from terrain that has been illuminated by directed beam of the pulses generated by the sensor. It means that SAR sensor transmit the electromagnetic pulses, and those pulses after interaction with the earth objects return back to the sensor, and finally the image is generated. Now when we are talking about the radar sensor, so we are using the polarized electromagnetic waves. Why? Because unpolarized electromagnetic wave or energy vibrates in all possible directions perpendicular to the direction of travel. So at that time, the return signal will have again the unpolarized vibration and unpolarized signal. So vibration will be in all the possible direction. So one will not be able to capture any information, or sensor will not be able to capture any information. A lot of noise will be there. So to avoid those things, to extract particular information of the target, polarized electromagnetic pulses or polarized electromagnetic signals are used. Radar antennas send and transmit and receive polarized electromagnetic waves or polarized energy. Here we are talking sometimes energy, sometimes electromagnetic waves. Both are same here. This means that the pulse of energy is filtered so that its electrical wave vibrations are only in a single plane that is perpendicular to the direction of travel. The pulse of electromagnetic energy sent out by the antenna may be vertically or horizontally polarized. Now in this slide, if you will see, so the first one is representing the vertical vibration or vertical transmit of the electromagnetic signal. Vertical according to the propagation axis. This is this red line is showing the direction of propagation of electromagnetic wave, and if the transmitted electromagnetic pulse will be vertically polarized, then this will be known as the vertical polarization, and at the time of receiving, again the the polarization will be broken. So after interacting with the objects, the electromagnetic waves will be start vibrating in all the possible directions. Some will be unpolarized, some will be vibrating in vibrating horizontally, some will be vibrating, some portion will be vibrating vertically. Now if the sensor is recording only vertical polarization, then this combination is known as VV. VV means vertically transmitted and vertically received. Similarly for HH, horizontally transmitted, horizontally received. VH, vertically transmitted, horizontally received, and HV, horizontally transmitted, vertically received. If a sensor is capable to provide all the polarimetric combination, then that sensor is known as fully polarimetric or quad pole sensor. Now there are different modes of SAR data acquisition: STIP map mode, spotlight mode, and scan mode. In strip map mode, one complete strip is covered by the sensor, and resolution will be the moderate, and the sensor will be fixed parallel to the azimuth direction. And in spotlight mode, when you will see, the SAR sensor will be fixed to a single point target, or to a small area, towards a small area during its full acquisition, so that the final image obtained from the SAR data will have number of returns, number of high returns, so that its resolution will become more fine. But the limitation will be the coverage or swath will become very less, very small. Now scan mode, SAR sensor will be captured, and this scan mode is also known as burst mode. So in this mode, SAR sensor will be transmitting the electromagnetic pulses, and using beam steering capability, it will cover a very large area. So if one will be interested to do the mapping and monitoring for very large area, like for flood mapping or for marine application, then definitely at that time one will be in need of the SAR imagery, which will have the information of very large area. So definitely at that time people are preferring scan mode data set. And spot mode, light mode, this is generally used for small object detection or identification, like for urban mapping and monitoring. Then at that time people are preferring spotlight data set. And for other applications like polarimetry and several other applications, people are using strip map, because generally polarimetric data set is provided, means all the polarizations are provided with strip map mode. There are a few geometrical distortions. So one is foreshortening. In foreshortening, layover and shadow. In all the conditions, we are getting shadow to opposite side of the terrain or opposite side of the feature. When the radar beam reaches the base of tall feature, tilted towards the radar, before it reaches the top, foreshortening will occur. The slope AB will appear compressed, and the length of the slope will be represented incorrectly. Generally, foreshortening is occurring in far range. And if the same hilly terrain will appear in near range, then the same hilly terrain will be giving the effect of layover. Layover occurs when the radar beam reaches the top of a tall feature before it reaches the base. The return signal from the top of the feature will be received before the signal from the bottom. So here in this case, the complete slope of the terrain will be covered by the top. So in the case of layover, one will not be able to get the information of the slope. And in the case of perfect shadow condition, in this case, the transmitted electromagnetic pulses will be incident perpendicularly to the slope, and finally this will be giving the complete shadow behind the terrain. And this is the example of or condition of the perfect shadow. In all the case, layover, foreshortening and shadow, we are not able to get the perfect information or actual information, but definitely there are some advantages of the shadows also. If you will see, if one will have the information of length of the shadow, one can easily find out the height of the target after knowing the length of the shadow, with the help of SAR altitude and ground range, and the formula can be easily seen here. Height of the target will be equal to the length of shadow multiplied by h divided by ground range. So at that time one will be able to get the information of height of the object also. When we are talking about optical remote sensing, then the reflected energy is used. When we are talking about the thermal remote sensing, then emitted energy is used. When we are talking about the microwave remote sensing, then scattered energy is used. So scattered or back scattered energy is used. So before that, we should know the different type of scatterers or reflectors. So if you will see the case of the first figure. So in the first figure, this is example of perfect specular reflector. Here, sensor transmit the electromagnetic pulses, and If the surface will be perfectly smooth like water or plain ground, then the whole radiation will be reflected away from the surface, away from the sensor. So at that time our sensor will not be able to capture any information, and these type of features will be appearing in dark because scattering will be very less. So our sensor will not be able to capture any back scattered amount. Now in this case, the second one is showing the near perfect specular reflectance. These type of surfaces will be showing some type of scattering phenomena, and some portion of the scattered signal will be returning back toward the sensor. And finally, these features will be appearing brighter than the perfectly smooth surfaces. Third is the example of perfect diffuse reflector or volume scatter. What is happening when the radar sensor transmit the electromagnetic pulses, and due to the roughness of these pulses, because different type of structures will be there like tree leaf, then small branches. So due to these type of structure, scattering will take place, and a good amount of scattered energy will return back towards the sensor. And finally, the appearance of these features will be brighter than the perfect near or perfect specular reflectors. Now the fourth one is the hypothetical surface, the case of Lambertian surface. So here in this case, this represents the equal distribution of energy in all the possible directions. So practically it is not possible, but when we are using the K band, so those surface with sands will be behaving like nearly perfect diffuse reflector or Lambertian surface. Now surface roughness, as we have seen in the basics of remote sensing, this is function of depression angle, wavelength lambda, and the local height of the object. And the first relation was given by the Rayleigh. So this is known as a Rayleigh criteria. According to that relation, if height of the object is less than or equal to lambda divided by 8 sine gamma, where gamma is the depression angle, then this will be known as the this will be known as the mm, smooth surface. Now when we are going to but this was not providing the good result in all the conditions, so again this criteria was modified by the Oliver. So modified Rayleigh criteria, you can see h for a smooth surface, h should be less than lambda divided by 25 sin gamma, and for rough surface it should be greater than lambda divided by 4.4 sin gamma, and for intermediate surfaces it is in between that. Now Now this is the this is the comparison between the smooth surface and the rough surface criteria for different wavelengths with different depression angles. So you can see here when you will put these values. So suppose in the case of aircraft Ka band, the object height, if the object height is greater than 0.27 centimeter, then that type of surface will be behaving like a rough surface. But the same object or the same surface will be behaving like a smooth surface in the case of L band. So here you can see that surface roughness is property of depression angle and wavelength and the object height. Now radar backscatter is also property of angle of incidence, because when angle of incidence will be increasing or decreasing, the intensity of return signal will also be increasing or decreasing. Now here you can see when the angle of incidence is low, so for the low angle of incidence, the maximum return will be there towards the sensor, and for larger angle of incidence, very less amount will be returning back towards the sensor. It means that if any person will be interested to extract the information below canopy, or for a forest area, if one will be interested to extract the information below canopy, then one should always prefer this low angle of incidence data set. Now the radar backscatter is property of angle of incidence. We have seen in the previous slide also, but here we are talking about the local angle of incidence, because when the surface will be smooth, the angle of incidence will be the angle between the transmitted electromagnetic pulse and the perpendicular drawn to the point of contact. So this will be the angle of incidence. But when the terrain is undulating, So the normal drawn to this surface is this one, that will be different. So in the case of undulating terrain, the angle of incidence will be different than the normal angle of incidence. So this will be known as local angle of incidence. To extract the exact backscatter amount, one should exact backscatter amount from hilly terrain, one should be able to extract the local angle of incidence also. So local angle of incidence information can be easily extracted from the external DEM. Using external DEM, one will be able to extract the information. Now in this slide here, you can see in the next slide how the backscattering is changing due to the change in the local angle of incidence. Like here, local angle of incidence is somehow in between middle. So here you can see the moderately bright patch is obtained, but for a small angle of incidence, very small angle of incidence, now here you can see very bright patch is obtained for very small angle of incidence. Now again, when angle of incidence is going larger, then here angle of incidence is very large. So here we are getting the dark patch, and again here we are getting the moderately dark patch due to the moderate angle of incidence or middle angle of incidence. So we have seen that. So that our backscatter is property of local angle of incidence also. Now we are going to discuss the interaction of the electromagnetic wave with soil. So here we can say that for mainly talking with the dry soil, wet soil and flooded soil. In the case of dry soil, penetration will be more, and finally less backscatter intensity will return back to as a sensor. So these type of surfaces will appear as dark feature. And in the case of wet soil, the large difference in electrical properties between water and air results in higher backscatter radar intensity. So wet soils will appear very bright in the SAR imagery. And again, in the case of flooded soil, the whole surface will be covered by the flood or water body. So one will not be able to extract any information, because no signal will be returning back towards the sensor, and finally these surfaces will be appearing as very dark feature. Now volume scattering, as we have already talked about the volume scattering. Volume scattering is the phenomena of scattering contributed by different components of the structure. Like in this case, first interaction will be there from the tree leaf, second interaction will be there small tree branches, then from big branches, and finally the whole structure will be contributing in scattering. And that type of scattering is known as the volume scattering. And here you can see L band will have more penetration due to the longer wavelength. So finally it will have the more information up to the ground information, because it will have the longer wavelength, penetration will be more. And C band, since it has the moderate wavelength, it will have the less penetration, so it will contain the less information of the whole structure. And X band is mainly interacted with the top of the canopy, so it will have the very less information of the structure. Now when we are talking about the complex SAR imagery, each and every pixel of the SAR dataset is represented by imaginary and the complex value, because here we are talking about the phase and amplitude of the electromagnetic wave at the time of interaction. So each and every SAR data is represented by the complex number. So here you can see there are two values for each and every pixel or for each and every resolution cell. Now this is the phenomena speckle. These are the unwanted bright signals. A SAR resolution cell generally contains a large number of scatter, and in comparison to the wavelength, this resolution cell appears very large. The returned echo from scatterer is coherently summed to obtain the phase and brightness of the resolution cell, sometimes due to a very strong reflector at a particular alignment, or due to the coherent sum of all the various responses. The resolution cell shows a brightness value which is much brighter than the actual brightness caused by the object. This unexpected bright value of the resolution cell is known as the speckle in the SAR imagery. So we are using the speckle filters. All the speckle filters are the low pass filters. A kind of averaging is done. So here you can see the second image is the image without speckle filtering, and the first image showing the speckle with speckle filtering. You can see a lot of variation is there in the imagery for the visualization point of view, because here you can see there is very less noise or absolutely no noise. One is able to clearly see the object and features in this imagery. So speckle filtering is required sometimes to extract the actual information. There are different SAR data formats: raw data, SLC data, excuse me, multi-look data, geocoded data, and polarimetric data. Raw data is the actual data set. It will have the signal information only, returns signal. SLC data is single look complex data set. Each and every pixel of the SAR data will be represented by complex numbers, and but it will have the slant and ambiguity also. When we are talking about the multi-look data will be uh, without slant and ambiguity, and better visualization will be there in this data set. Geocoded data set will have the geographic coordinate information, and polarimetric data set will be dealing with the different polarizations. There are different applications of the SAR remote sensing in each and every field of the natural sciences and the earth resources. So here you can see for soil moisture, biomass, crop, flood, oil spill, DM generation, subsidence monitoring. There are glaciological application. There are different applications.